Now we're going to talk about probably the most important concept of time series, and that is randomness. Our aim is to ultimately end up with data that has only the randomness once we remove the components of, say, trend and seasonality. And in that case, once we're able to do that, we will then have a data set that we can look and see what other variables are impacting the data beyond just the general trend. So our forecast models will have, in the general form, a predicted value, y, plus equaling a fitted value, plus some error term, just as our regression models had done in previous modules. The fitted value is provided using the previous data and other attributes, leaving only the residual term, which corresponds to the error of the prediction. So from our regression notes, our aim is to have residuals that are independent and random, which we will term noise. So we're going to examine randomness three ways. We're going to examine them graphically. We're going to use another test called the runs test and another test called autocorrelation. Now, in graphical terms, we can assess the randomness by clearly looking at the graph and seeing if there's a pattern. If there's no obvious pattern, then we probably have randomness. And it's a good idea to analyze the graphs first, just so that you can get an idea of what type of pattern might be there. Is it a straight linear trend? Do we sense their seasonality? Is there an exponential trend? Or does it look like it has the possibility of being random? So our goal is to basically have a graph looking like this one, where it is simply just noise and a random pattern. Now, in the runs test, we have a statistical hypothesis test to measure whether a set is normal or not. The procedure is fairly easy, but the calculations in Excel are a bit cumbersome. So in statistical applications like R, it's much, much easier. The runs test basically assesses a series of numbers above or below a certain threshold, say, for example, a median. So we're going to create a data set that has an increasing trend from 1 through 20, and you choose the median 10 as your breakpoint. In this case, the runs test is going to calculate a series of numbers that are below and above the median. And in this case, we'd have two runs. So what we're doing is this. For every time that a number is below or above the median, every time we shift or cross that boundary, we will basically say a new run is beginning. So you can see here that if we had the numbers 1 through 20, 1 is below the median, 2 is below the median, so they're all part of the same run. 3 is below the median, all part of the same run. But once we get above the median and we cross the line, we then start a new run. So in the numbers 1 through 20, you would have only 2 runs. Now, if you had a data set where each successive number was above and below the median, such as 1, 11, 2, 12, every time we cross the median, we end up with another run. And so therefore, we would end up with 20 runs. Thus, if you have too few or too many runs, the data is really not random. There exists some pattern. So we can compare the number of runs to a standardized normal distribution to assess whether the number of runs provides evidence of randomness. So let's see how that works. So here on the right side, we have a set of data, and we've calculated that the median is 51. First, let's set up the hypothesis test. The hypothesis test is that the null hypothesis is the data is random. The alternative hypothesis is the data is not random. Therefore, in this hypothesis test, we're looking for the p-value greater than 0.05 so that we do not reject the null hypothesis. Each time the numbers cross that median, we will then increment the run number. So you can see here we have 25, that's our first run starting. 14, 37, 29 are all below. Then we hit the median, so we'll consider that crossing, and we'll move that to the next run. Then we come below the median, and so we'll consider that a new run. And then you can see each time 63, 47, 55, we are crossing the median again, and so we'll attribute it to the next run. We calculate all those, and we end up now here with 16 runs. Next, we need to identify the following: the total number of runs above, and the number of runs that are below the median, which we've classified as ones and zeros. The mean of the data set is going to be given by 2 times the number of runs that are above times the number of runs below, divided by n plus 1. Now, this mean is actually the expected number of runs, and that's what we're referring to here as the mean. The variance of the data, or the variance of this data set in terms of the runs, is given by the following below. Once we do that, we will calculate the standard deviation by taking the square root of the variance. We'll compute a z-score using our Excel functions there on the right, and then we'll compute the p-value. So as you can see here on the right, when we've computed the z-value and the p-value, our p-value is now 0.86. That 0.86 is greater than 0.05, and therefore we do not reject the null hypothesis, and we can say that the data set is random. Another measure to determine the randomness is to see if previous periods are related to the current period. In order to examine this, we're going to need to push down the data and create what are called lags. So in this data set here, you can see that the lag is created. A lag 1 means we're pushing the data set down. And in Excel, we're just copying the data one row down. A 2-period lag would basically push it down 2 cells, 3-period lag 3 cells, and so forth. And in this example, we have 10-period lag. Once we've done that, we'll use the data analysis add-in in Excel to compute the correlation, or you can use any statistical software that you have to do the same. We'll have a corresponding video on doing this in R as well. This will give us a table that will look like the following. And we're really interested only in the first column of correlations because we're looking to see the correlation between the periodic lags, which are on the left, 1 through 10, and the original value, which is NASDQ. And here you can see that we have 0.14, negative 0.08, 0.17, and so forth. And these correspond to the correlations. Now what we're going to do is we're going to chart this out. And when we chart this out using a bar chart, we're only going to chart the first column. So our aim is to look for any bar that is significantly high. Now, what value is significantly high? Anything over 0.25 or below negative 0.25 means that we probably have an autocorrelation problem and the data is not truly random. However, we can be a little bit more specific by calculating a confidence interval. And this graph down below is actually what's called an ACF or an autocorrelation graph. And you'll see that in statistical applications as well. The confidence interval for the correlation is measured by a z-value. Since the alpha value that we're looking for is 0.05, we're looking for a score at 1 minus 0.025. And this is given by the Excel function norm.s.in, or the standardized normal, 0.975. Again, these are for the two tails. So our formula in Excel is given in our third row down here, where you take z divided by the square root of n. That's our z value. So for example, lag 1 has 60 data points, lag 2 will have 59 data points, and so on. The confidence interval for the correlation, again, will be plus or minus 0.25 for lag 1. But notice that as the lags get bigger, in terms of the further lags we get, lag 2, lag 3, lag 4, there are less data points, and what ends up happening is that your z divided by the square root of n slowly begins to increase. And that's why we say generally 0.25 is the number that you're looking for. So anything above 0.25 or below negative 0.25 is going to be considered an autocorrelation problem.